All right, welcome back to the next concept, and now we are moving on to combinations. So in the previous six concepts, we have been talking about permutations, and now we're going to be jumping over to combinations. So just as a recap, right? Combinations basically means that we are arranging things, right? But now the order does not matter, right? So in simple language, right, simple English, it basically just means that now it's who is part of the group, right? It's more on who is part of the group that we are focusing on rather than who and in what order is the group in, right? This is not what we're focusing on. This over here is my combination concept, but then this over here is my permutation concept. So now we're just going to be focusing on who is part of the group. So let's just use this as an example, right? Assuming again I have 5 different alphabets, A, B, C, D, E, right? So over here I have 5 distinct objects, but then I want to pick R objects. So let's say I want to pick 3 out of 5. So this 3 out of 5 over here, right? The order does not matter at all. So how do we actually pick this 3 out of 5? In your calculator, you can basically just key 5 choose 3 in your calculator and it will give you the final answer basically, right? But how do we actually derive the formula for this? So it's a little bit of a reverse engineer from the previous concept, right? For instance, remember in the previous concept, you learned that, okay, so I'm just going to draw from the previous concept. So previously, in permutations, right, in order to pick 3 out of 5, where the order matters, what you did was you took 5 times 4 times 3, right? And then the times 2 times 1 over here is being cancelled out by the 2 times 1 at the bottom, right? And then previously you learned that the formula was your n factorial over n minus r factorial over here, right? But this over here is for your permutations. But now, the difference between permutations and your combinations is that the order does not matter now, right? So this formula over here that we learned previously, it takes into account the order, right? So if I were to write it below over here, right? Previously, n factorial over n minus r factorial is basically the number of ways to choose 3 from 5 objects where order matters. But right now, what we want is we want the number of ways to choose 3 from 5 objects where the order does not matter. So how does this actually apply for us, practically? In the previous formula over here, they treated A, B, C differently from C, B, A, right? These two are treated differently here. Yeah, maybe I just put it this way. AB and BA are treated differently over here. But now, for the bottom one, now we want to treat AB, BA the same. That means we want to group these two as just one item. So the only difference between the top formula and the formula in this portion over here is that we're going to be using the same exact formula as above, right? But this time, we are going to divide away the r factorial because now for the next, or rather for this portion, we want to divide away the number of ways to arrange the R items. Because when we eventually divide the R factorial away from the number of ways to arrange the R items, we end up with a number that gives us the total number of combinations without the arrangements. And that's how we achieve this formula, which is basically what happens in your calculator under the hood, right? What your calculator does is that it just takes 5 factorial over 5 minus 3 factorial, 3 factorial over here, right? That's all it does basically, is that it computes it using this formula over here. But now you know how it works, right? It's basically what we did in the previous videos, but now we divide one more step, right? We divide away the R factorial to treat all of these different permutations the same as one single combination, because now it's not so much of who and in what order, it's just who. So in essence, for this portion over here, right, the formula is n choose R, right? N objects choose R distinct objects, and the formula behind this would be your n factorial over n minus R factorial multiplied by R factorial in the denominator to divide away the different number of permutations, right? So yeah, that's it for this concept over here. Let me know if you have any other questions. If not, we will be practicing this in the next section over here. Make sure to pause this video over here first to tackle the questions. Pause it right now, tackle it, return when you're done. If not, I'm going to be assuming that you're done, and let's jump right into this question. So for A over here, right, we have 13 female and 7 male students in the class. So immediately we know that all of them are distinct. So I have 13F and 7F. 4-member committee is to be selected. How many ways can it be selected if there's no restriction to the selection? So if there's no restriction to the selection, 13F plus 7 male gives us a total of 20 distinct students, right? And you know, if there are 20 distinct students, we want to choose 4 out of the 20. So this over here is as simple as just punching into your calculator the value of 20 choose 4, right? 20 choose 4. And when you punch this into your calculator, you get a value of 4845 as the final answer over here, right? 20 choose 4. And of course, you will know how the formula works. It's just this, but honestly, in the exam, you know the concept, just use the formula accordingly, right? So that's the answer for the first part. Now, the next part is that there must be at least 2 female students in the committee. So what this means is that we have 4 slots over here, right? There must be at least 2. So it can be, you can have 2, you can have 3, or you can have 4, right? So for these type of questions, right, now I'm going to be teaching you a method, which is whenever you see the word at least, to tackle these type of questions, you would want to, usually, you will want to consider the complement. So you can see that there are 4 possible cases, right? Or there are 5 possible cases actually. There can be no females, 1 female, 2 female, 3 female, or 4 female, right? In the selection of the 4 committee members. When we say that there are at least 2 females, that means we want to take this into account, this into account, or this into account, right? You can take these 3. So of course you can manually compute the 3 ticks that I've just left on the PDF. Alternatively, you can just take the total number of ways of arranging all of these, which is basically 4845, and then you minus away this and this, right? So since you already know the total number of ways is 4845, you just need to minus away no female and minus away 1 female to give you the rest, right? So this is the method of complement. And the reason why we use complement in this case is because lesser steps, because you just need to compute 2 things rather than 3 things, right? So if there is no female, that will basically means all male, right? And all male, which means that we have 7 male, choose 4. Because now out of these 7 males, 4 of them will be chosen to be part of the committee, to fill out the 4 people committee. So we know that for the case of no F, is 7 choose 4. Now, in the case of 1F over here, 1F means that you have 3M and 1F, right? So given that we already know we have 1 female in the selection, that means how do we choose the 3M and the 1F? So it will be as simple as taking 3, or rather we have 7 males. So 7 males, choose 3. And 13 females, choose 1. Right? So when we compute these two like that, right, this is the first case, this is the second case over here. To answer double I over here is as simple as just taking 4, 8, 4, 5. You minus away your 7, choose 4, right, which is the first case. And then you minus away the second case, which is this over here. Right, so you minus away, I'm just going to rewrite this whole thing over here. You just minus away 7, choose 3 times 13, choose 1. And eventually, you get a value of 4355, right? So I'm just going to put these two back, right? No F and 1F over here. So this method of complement is actually very, very useful whenever you need to consider multiple cases, right? And when there are multiple cases, the easiest way would be to just find the total number of cases. In this case, is 4845. Then you minus away the complements, which is the cases that are not part of the bigger case. Okay, so this is the answer for double I. So you can see that while the formula you have been taught by me, it can be used in this question, you can also use techniques to use the formula. So techniques and formula are two different things. Okay, now for B, how many ways can the 20 students be divided into two groups of 8 and 12 students each? The thing is that for this question over here is slightly more interesting. Why? Let's start with BI first. So imagine I have 20 students, right? When I split them, let's say I choose the first 8, right? Automatically, the remaining 12 will fall into the second group, right? So the idea behind this is that when you choose the first 8, right, the last 12 will automatically result in the second group over here. So the total number of ways that you can divide the 20 students into these two groups would be to just take 20, choose 8. Because when you take 20, choose 8, the remaining 12 will automatically be in the last group. And therefore, the answer to this would just be 125,970 ways over here. Right? So this is part B. You don't need to compute 12 choose 12 again. Right? And even if you did 12 choose 12, you get a value of 1. Right? So it's not really that necessary. But of course, if you took 20 choose 8 times 12 choose 12, you will also get back the same value over here. Right? But this step over here is not really necessary. Right? Especially when you're first learning the chapter, you want to make sure that every step makes sense to you. Now, last but not least, we have 10 students each. Now, this last case over here is slightly more interesting. Why? Because imagine this, I have 20 students, right? And these 20 students, when I split them into the first 10 and the next 10 over here, right? When I choose the first 10, automatically the next 10 will be decided, right? But the thing is that these two groups have the same size. However, this is a very important thing to note, is that whenever you are dealing with questions with equal group sizes, there tends to be a scenario of over-counting risk. Okay, let me just paint this picture for you to see. So let's say this is group 1, group 2, right? Let's say this is student 1 to student 10. And then let's say this is student 11 to student 20, right? So far, not wrong, right? You choose the first 10, the next 10 will automatically be slotted into group 2. However, it could also be the case whereby it's S11 to S20 over here. Yeah, let me just say, right? It could be S11 to S20 over here. And then for the bottom group, it could be S1 to S10. Right? And when you key into your calculator 20 choose 10, right? It could be either scenario. But the thing is that these two are exactly the same, right? Because it's whether you are labeled as group 1 or group 2 only. But the thing is that when you key 20 choose 10, it takes into account these two possibilities. So there is double counting over here actually. So the answer to this is basically just your usual 20 choose 10, right? But you need to divide away 2 factorial because these two groupings are identical, right? This one and this one, these two are identical. And whenever we have two identical objects, we need to divide the 2 factorial away, simply put. Okay, and with that said, your final answer over here will give you a value of 92378 as the final answer to this question over here. Okay, so that's it for combinations. This question over here is a mastery question, so if you got any other questions, let me know in the comments below. If not, I'll see you in the next video for the summary of this chapter and to wrap things up for this chapter for S1. If not, I'll see you in the next video.